Alright, so today's video we're going to do an introduction to a second type of word problem that you see in calculus, which is what is called an optimization problem. Now, to contrast this with what came prior to this, which would be the related rate problems, in a related rate problem you were given information about how fast objects or quantities were changing, and then you were being asked to determine how fast a certain quantity was changing with respect to time. And so it was a related rate problem because you first had to identify a quantity formula, then you took your derivative implicitly with respect to time, and then used the rates, their changes with respect to time, to plug in the values that you know for a certain instant to find the speed that you were asked to investigate. Now, optimization, those are a different class of word problem. In these problems, we're not concerned with how fast the quantity is changing. What we're trying to do is to figure out when the quantity is at a maximum or a minimum. When it's the biggest, when it's the smallest, when it's the cheapest or the strongest, or, ugly as we're just trying to be funny here. But what we're trying to do is we're trying to optimize, to come up with an ideal situation, which means we're looking for extrema on the graph. And so this is why this is in chapter 4, which if you look back at our beginning, 4.1 to 4.6, all of that is about trying to determine the extrema of a graph. Now, usually what happens is you've got some quantity that's changing, and there must be some constraint or a limiting factor. So in an optimization problem, instead of like in a related rate, you determined what speed you were interested in, and then you went to go find other speeds that you knew. That's why it was called related rate. Now you're going to identify what quantity you want to max or minimize, and then you're going to go find a constraint, a limiting factor that is going to constrain the quantity from growing without bound or decreasing without bound. Now, in this unit, we are going to be looking for absolute extrema. However, we will not always have endpoints. And so while EVT is going to be kind of a first rule that we're going to use if there were a closed interval, we're going to have to use a modified first and second derivative in order to create tests that we can use that will take care of absolute extrema. So we're going to do a modified first or a modified second derivative test here. All right, and so that'll give us our 3 different methods that we are going to use to actually find this global extrema that is our target. And again, we're going to try to keep it easy, keep it simple. We're going to always go with the justification method that is the least amount of effort. We want to keep it simple and keep it as efficient as possible. Now, of course, these are challenging problems. I'm not going to lie to you. They are word problems. But hopefully, now that you've seen how the related rate problems work and what the target was there to determine how fast something was changing at a certain instant in time, that as soon as you read through an optimization problem and you realize that they're asking you to find the least or the greatest or maximize something, that you know that it's going to be an optimization problem. All right, we're going to outline the steps briefly, and then we'll kind of jump right in. One cannot say anything more about trying to make sure you read the problem carefully, as we've learned in our exam, being very cognizant about what they're asking you to do and what they're given. Drawing a picture is always going to be good to help come up with relationships. When you go to find your equation that is going to be what you're going to optimize, whether you want to optimize profit or you want to optimize your area, you have to come up with an equation. Now, a couple of things about when you're coming up with your formula, when you're using the drawing, the picture, and trying to determine what's being optimized to come up with this primary equation for your quantity. So you're going to get a quantity formula just like we did before. A couple of things that I want to kind of point out here, that if you can, when you are labeling your diagram, label small parts as your variables so that the larger part is going to be in a sum instead of a difference. Like, for example, if I had a length and I knew that portion of it was 10, and then I basically have 2 variables in the problem, the entire length and then this short length right here, you want to make your variable typically the shorter one, so that this would become x plus 10, instead of making this y and then making this y minus 10. It's just a fine nuance. It just typically does always work out to be a little better for us to keep that in mind as we are labeling our pictures. Once you have gotten your primary equation, the quantity that you want to optimize, then you look for secondary equations. These are going to be things that relate inputs into your formula. For example, if I know that my volume is 4/3 pi r squared h, then my input variables are r and h here. That's a fine primary equation, but I prefer when I take my derivative to not have both r and h in here. So usually you're going to read through the problem and you're going to be looking for another relationship that will relate maybe your radius and your height together. It may be that your radius is always half your height or something like that as an example. And so what you can then do is substitute this into the primary equation and basically get yourself down to one input variable and one output variable. And so that's always going to be our target when we're looking at that. So 4 and 5 go together. You're going to solve this secondary equation for a convenient variable, and then you are going to substitute it. That's the whole idea of this. You are going to substitute to simplify the quantity equation. A lot of times students have difficulty with this. Sometimes they try to think of this as their quantity equation that you're going to take the derivative of, but it is not something you're going to take the derivative of. It is something that you are going to use to simplify your quantity equation in the problem. And a lot of times it doesn't matter, because you could either say r equals 1/2 h or h equals 2r. You're going to have some options here, and so usually you would go with whatever makes it the easiest. Like here I would probably substitute for h, because then it makes it easier to take a derivative. It's always about planning ahead and thinking about what is the easiest thing to do that is going to give us the quickest and fastest way to optimize. Now, in looking at this, kind of the steps that we've outlined so far are read the problem, draw the picture, determine what's being optimized, identifying your constraint that you're going to use, solving the secondary equation for a convenient variable, and then substituting it and simplifying, actually all the way down here to 6, that all of these kind of steps are really nothing more than you doing the setup of the problem. And so it's going to allow us to get ready to do the calculus, to identify the problem, the variables, the relationships, and to set it up so that we're ready to use calculus in order to answer the question that we had. So calculus doesn't come into play until we get down here to 7 and 8 and 9. Once we have our primary quantity equation, we would then differentiate, and hopefully we've managed to set it up so that it is easier to differentiate. Then we are going to determine the absolute extrema, and that is going to be basically using your three options. You either are going to use your EVT and then or your modified first derivative test or your modified second derivative test in order to do it. And then at the very end, as always, you want to make sure that you answer the question in a complete sentence using your appropriate units. All right, now let's take a look at our three methods, the EVT, modified first and modified second, before we actually jump into any problems. So let's take a look at method 1. That's the one that's probably the easiest for you to remember. Your closed interval argument. Remember that you want to make sure that in order to use method 1, your function must be continuous on a closed interval. Now, typically, when you are doing these problems, you will not be given a closed interval. However, it's when you have relevant endpoints. What that means is in a real-world problem, you are going to figure out a relevant domain, which is the domain that makes sense in the problem. And if your relevant domain is a closed interval, then we get to use the EVT, where we create the table of values with our function using our endpoints. So we would do A, B, and then any critical values in between, and then we would choose the largest or the smallest. All right, now, unfortunately, even though we like EVT and we would love to use it every single time, it does not work every time. It only works if you have these relevant endpoints from your domain. But if you do not have a closed interval with a continuous function, what you can do, however, is modify your first and second derivative test. Now remember, your first derivative test is for relative extrema, but you can modify it for absolute extrema. You're going to start it the same way, differentiate, and find your critical values. You're going to then determine if the function always, here's your key word, always increases before and decreases after your critical value, okay? And that if you have this one critical value and you've got it always increasing before and decreasing after, then you would have a global max. Or you can switch it and say if it decreases before and increases after, then you would have a global min. But it has to be for the entire relevant domain that you have this. If there's any switching, if it's increasing, decreasing, increasing, then you're out. You have to make sure it's always doing one or the other, and you can split it into two sections basically. Method 3 is your second derivative test, and again, reminding you that that second derivative test was only for relative extrema, but we can modify it for absolute extrema, which is you find your first derivative just like you do up here, you find your critical values of your first derivative, where your first derivative is equal to 0, and then you find your second derivative, and you want to make sure that it's easy to obtain, otherwise there's no point to do this. And what you want to do is determine, and again, the key word here is always. If the function is always concave down, you have a global max at the critical value. And if it's always concave up, you have a global min at your critical value. And it has to be concave up for all x in your relevant domain. Right? And so the idea is instead of basically getting in the first derivative test for relative extrema, it had to be a critical value, and the first derivative had to switch signs. Now you need it to be a critical value, and it has to always be positive before and always be negative after. Okay? And then in the second derivative test for the extrema, it has to be a critical value, and it has to always be concave up or concave down on that relevant domain. Right? So now let's go and let's take a look at a few simple examples in this, and you'll kind of see they work from hard or easy to hard. We kind of are starting with the easiest ones, and we're going to work our way up. So I'm reading the problem. Find two positive numbers whose sum is 60 and whose product of one times the square of the other is a maximum. So the first thing you're going to look at is that why is this not a related rate problem? They're not asking me to find out how fast the numbers are changing with respect to time. It has nothing to do with time. What I'm trying to do is determine a maximum, and I'm trying to maximize the product. Okay, so your first step is you have two numbers. Usually when you're doing this, you might have to define some variables. So I'm going to do x and y. So x is the first number, y is the second number. Okay, just to give myself some variables to work with. There's no pictures to draw in this one, but I do know that I want to maximize, so I say max, and what I'm trying to maximize is the product. So I do product equals, and now I go find a formula. So my formula for my quantity formula that I am going to use as my primary equation, the product of 1 times the square of the other, 1 times the square of the other. So x, y squared. So this creates my primary equation. This will be the one that you will eventually take the derivative of. However, we do not want to take the derivative before we simplify it. So we're going to go look for a constraint, something that gives me some information about x and y, which are my two input variables. So I look up here and I read the rest of the problem, and I see that we have the two positive numbers whose sum is 60. So we know that x plus y has to equal 60. So what that does is that gives me something that I can use to either solve for y or solve for x and then substitute. Now we're going to make a decision about which is going to be better for us. If I solved for y down here and then have to substitute 60 minus x in, I'm going to have to square that and FOIL. If I solve for x, I get x is 60 minus y, but there's no power on the x. That one is going to be easier. So I'm going to solve this for x. Then I am going to use that constraint, okay? The whole point of the constraint is to take our primary equation and simplify it. So we're going to plug this in for x, 60 minus y times y squared. And then, if I can, go ahead and simplify this to a nicer form that's easy to take the derivative. Since this, you could use product rule, but why don't we just distribute and just use power rule? So we have 60y squared minus y cubed, something easy to take the derivative of. Now we are ready to do the calculus. All of this from here to here was simply setup. All I was doing was trying to figure out what I was going to take the derivative of. So now we're ready to actually work the problem and do the calculus. We're going to take the derivative of our primary equation. And now this is another big difference between related rates. I am not taking the derivative with respect to time. You are always taking the derivative with respect to whatever input variable you have. So we're really, if you're thinking about this, doing dp dy. We're taking the derivative of p with respect to y. And because we're not really worried about the whole related rate problem, and we're always going to be taking the derivative with respect to our input variable, a lot of times instead of saying dp dy, we just write p prime, because it's very clear what we're doing. We're taking the derivative with respect to whatever variable is over here. Our derivative would be 120y minus 3y squared. We then determine our critical values. So critical values when p prime is equal to 0. I can factor this. We can pull out a 3 and a y, and that's going to leave me with 40 minus y. So those are y equal to 0 and y equal to 40. Now I'm going to pause because I forgot to do something that I should have done before I went to do the calculus. I should have figured out my relevant domain, because I should know what strategy I want to use. Do I want to use EVT, modified first, modified second? Now, in this problem we have two numbers, and you want to pay attention to this. They are two positive numbers whose sum is 60. Now, if you're adding two positive numbers together to 60, first off, I can't be 0, and I can't be negative. So we're going to have to start above 0. Now, there's nothing that says I can't be fractional. It just said it had to be positive. So I'm going to start at 0, and then obviously the biggest that you could be is 60, but you can't actually be 60 because then you would have to do 60 plus 0. So it's going to have to be a number less than 60 added to a number less than 60, and they both have to be positive. Now notice that we do not have a closed interval, so this is not EVT. So at this point, when I am doing my strategy, I know I'm either going to have to do modified first or modified second derivative. I'm going to go ahead and just do modified first for this. And modified first says, well, first we're going to determine positive and negative. And we have to always be, now we're going for a max, right? So if I want to be a max, I have to be always increasing before and always decreasing after for the quantity function. So I need my first derivative to always be positive before the critical value and then always negative. Now, once I have my relevant domain, this 0 is not even a candidate because it's not in my relevant domain. I'm really only considering, so when I'm looking at my sign chart for this, I'm going to start at 0 and go to 60. However, I am only interested in the 40 as a critical value. Now, unfortunately, they don't let you say, stop, it was the only one I had, so therefore it must be the max. Because you have to justify with calculus, you are going to need to take it a step further and say, well, even though that's the only candidate right now, and it probably is going to be the max, I have to justify with calculus. If I were to plug in, now remember, just kind of, this was 0, this was a 0 on my derivative p prime. 60 I only have on here because it's an endpoint. Right? P prime is a negative lead coefficient quadratic, so it's negative, positive, and then negative, and technically it's also negative over here and negative at 60. But we are only concerned with the portion that is from 0 to 60. We don't care about what happens anywhere else. And notice that as you are looking at this, that From 0 to 40, the first derivative is positive. From 40 to 60, the first derivative is negative. So it's always positive on the relevant domain before the critical value and always negative after. And so that's what I need for the modified first derivative. All right, so now I'm going to answer the question. All right. So, and then also I go back to make sure what the question is. I need to find two positive numbers. So we would say y equal to 40 and x equal to, they have to sum to 60, so 20. Maximize the product because p prime equals 0 when y equals 40 and p prime is greater than 0 for y in the relevant domain of 0 to 40 for before, and p prime is less than 0 for y in the relevant domain 40 to 60. That you're getting the before and the after, and that is the relevant domain. Okay, let's take a look at another example. We have an 8-inch long pipe cleaner, you know, those little bendy little things, and we're a little picture over here, and we're going to form a rectangle. And it's going to be bent into the shape of a rectangle. And we want to find what dimensions of the rectangle will produce the rectangle with the maximum area. So again, not a related rate problem. They're not asking me to see how fast the area is changing given some other information. They're asking me to maximize the area. So just like we did before in our setup, we're going to go, I want to maximize. What do I want to maximize? Area. It's area of a rectangle, which is going to be length times width. So sometimes a picture is going to be worth a lot. So we're going to have our length. We're going to have our width. Now our constraints. So we have our primary equation. So now we go looking for some constraints. What is going to give me a limit on the pipe cleaner? Well, my length and my width, obviously, because it's an 8-inch long pipe cleaner, my length times 2, because my perimeter, plus 2w has to equal 8 inches. Okay, I can't form a rectangle that has more perimeter than 8 inches because that's all I have in my one pipe cleaner. So we're going to take a look at our constraint. Now we have a choice. We're either going to solve for L or solve for W. It doesn't matter in this case. It's exactly the same either way, so pick your favorite letter. I'm going to solve for L. So it would be 8 minus 2w divided by 2, or 4 minus w. Now, the whole point of that, again, remember, your constraint is to simplify your primary equation. So our primary equation is going to become 4 minus w times w. And again, better to simplify early and often, so I'm going to rewrite this as 4w minus w squared. And so that's what we're going to maximize. Let's be smart this time and let's find a relevant domain before we start. Now, obviously, in order to have a rectangle, you have to have a length or width, so it's going to have to be greater than 0. And you have to have, you can't have 8 as your width, because if you had 8, then you wouldn't have anything left to actually make a length. So it has to be less than 8. So our relevant domain is 0 to 8. Again, no closed interval. You cannot use EVT. All right, so we're ready to go. We know that we have to use modified first or modified second. So we're going to take the derivative and find our critical values. This step is almost all the same in the first ones. So my a prime, and again, remember we're taking the derivative with respect to w. We're finding dA, dw. We are not finding it with respect to time because we're not doing a related rate problem. We're doing a maximization, minimization problem, an optimization problem. All right, so our derivative is going to be 4 minus 2w. So my critical values, your derivative is equal to 0 when w, if you subtract 4, divide by 2, w equal to 2. Right? Now, in this case, just to show you a little alternate here, let's actually use the modified second derivative here. just to contrast what the difference is between the two. So in the modified second derivative, I've got my critical value. Now I am going to take the second derivative. So easy to get. The second derivative would be -2. And notice, that's the key thing here, that the second derivative, a double prime, is less than 0 for all values of w in the relevant domain. And that is what we need for our second derivative test. That if the second derivative is negative, then we know that our function on the relevant domain is always concave down. And concave down always means you must have a global max. All right, so let's go. Now let's answer our question. Let's see what they actually asked me to do. They want to find what dimensions of the rectangle. What dimensions of the rectangle. So the dimensions of a rectangle that maximize area are width equal to 2, what units are we in, because that's always important, 2 inches. And my length is going to be equal to 2 inches. And you might be like, I already knew this. That's okay, we're starting with really easy problems. And then because, use our calculus, w equal to 2, let's say 4, w equal to 2, a prime of 2 was equal to 0, and, so it was a critical value, a double prime is less than 0 for all w in our relevant domain. So A is concave down, and w equal to 2 is a global max. Okay, so again, set up your primary equation. Once you have a primary equation, you look for your constraints. You use your constraints to do a substitution so that you can simplify your primary equation. So you have one input. Once you have one input, you take your derivative. And then, because our relevant domain was an open interval, we had to use either modified first or modified second. We chose to use modified second here. All right, let's take a look at the next example. All right, so example 3, they like problems like this. We have a farmer, ladybug farmer, 500 inches of fencing, wants to fence off a rectangular field that borders a straight river. Now, you want to be very careful when you are kind of drawing this, that you realize that when you are fencing, that you don't fence along the river. There's no point to do that. The river is a boundary. Okay? So he needs no fence along the river. They can't swim. He's clipped their wings. They can't fly. And they want to know what are the dimensions of the field that have the largest grazing area for his ladybugs. So again, they're not looking for a speed or a rate. They're looking for the largest grazing area. So we identify that we want to maximize our area. Okay. We need some variables, so let's label our length and our width here. So area is length times width, so nice and easy. Start looking for some constraints. We see that we have to have some relationship between L and W, our two inputs. We see that we have 500 inches of fencing, so L plus W has to equal 500. And again, does not matter which one we substitute. I'll do W this time. So we then use this to substitute, create our primary equation. Area equals length times 500 minus L. I'm going to simplify, make it easier to take the derivative. I'm going to figure out my relevant domain. In this, we have 500 inches of fencing. Our length and our width, so our length has to be bigger than 0, can't be negative, and it has to be less than 500 inches. Now, obviously, we know it's going to be somewhere in the middle, but we have to include all that. Again, not an EVT problem, so we're going to use either modified first, modified second. I'll make that decision after I start taking my derivatives. So now we start the calculus. Our A prime is going to be 500 minus 2L. And while I'm here, I think it's going to be nice to go ahead and do A double prime equals negative 2 again. And again, I'm going to use modified second because A double prime is less than 0 for all lengths in the relevant domain. So I can use that modified second derivative. My critical values, A prime is equal to 0 for L equal to 250. Okay, and pretty much at this point we can answer the question. The question they're asking for are the dimensions. So the dimensions of the field with the largest grazing area is a length and width of 250 inches because, there's our calculus, A prime of 250 was equal to 0 and A double prime was less than 0 for all L in the interval 0 to 500. You almost don't even need to go to the, you don't have to say A double prime less than 0 for all L, so A is concave down and L equal to 250 is a global max. You can almost get away with saying, once you do this and talk about it being less than 0 for all, that you automatically get that as your conclusion. All right, now example 4, same situation. We have our ladybug rectangular fence we're going to make along the river, except now these diva ladybugs require exactly 10,000 square inches of grazing, and they want to know what is the least amount of fencing required to get them to their optimal state. So again, you start with what you're trying to max or minimize. Now I'm trying to minimize the amount of fencing. Amount of fencing is your perimeter. Okay, so if we have our length and our width, and I'll put a width over here, we're going to minimize our perimeter, which is equal to 2W plus L. You look for your constraints. Okay, in your constraints, what we know is that we have exactly 10,000 square inches of grazing. Square inches, that's giving you an area. So we know that the area, which is length times width, is going to be 10,000. So that is our constraint that we're going to solve. Now, in terms of simplifying, I would probably just solve for L. It'll probably be easier. So we have 10,000 over W. We do our substitution. So P equals 2W plus 10,000 over W. And just because I think it's easier to take the derivative, I am going to write that as 10,000 W to the negative 1. I'm going to figure out my relevant domain. And our width, again, we have to be larger than 0. And now this one, let's talk about how big we can be. Our constraint is on the area. Our width and our length have to be positive numbers. How big can W get? Can W be 100,000? Yes, as long as L is 1. Can W be 200,000? Yes, as long as L is a half. And that's okay because it can be a small length. Won't be likely for an optimization, but could it be? Yes. Could I be 2 million? Well, yeah, as long as L is 1 over 2 with a whole bunch of zeros in it, that's going to cancel them out. So really the idea here is it's 0 to infinity. So we don't even have an interval. We just basically have 0 to infinity, not 0 to a number. But that's okay as long as we use modified first or modified second. So now we're ready to start. We know we can't use EVT, so we're going to do our calculus. We're going to take our equation, our primary equation, our quantity equation for the perimeter that we're going to minimize. Be careful you're minimizing this time. So our derivative would be 2 minus our 10,000 w to the negative 2. You actually should like these better than related rates because you don't have the whole implicit differentiation, follow it with dw dt, because we're not taking the derivative with respect to t anymore. Let's see, what do I want to do for our critical? I'm going to go ahead and just use the modified first derivative here. P prime is equal to 0 for, and again, just to rewrite this in a nicer form, it would be 2 equal to 10,000 over w squared. W squared equals 5,000. So W equals, remember it's positive, square root of 5,000, which you could simplify if you want, but it's not necessary. If it was a calculator problem, you would round to 3 decimals, but it's not. If you wanted to, I mean, just for, hey, let's pre-calculus have fun simplifying, you could. This would be 100 times 50, or 10 times 10 squared times 5 squared times 2. So 10 times 5 is 50 square root of 2. But either they'll take square root of 500. Now once I have that, now let's think about our modified first derivative. We're doing this. If I was to do a sign chart for the first derivative, p prime, starting at 0, and our critical value is going to be this 50 square root of 2, which we know is 0. If we plug in a number over here, remember this is like 1, let's plug in 1. That would be 2 minus 10,000 over 1. Obviously, that's going to be a negative number. If I plugged in 0, which I can't because that would be not allowed, right? But we don't worry about that because I don't care about 0. I only care 0 and above. And then if we pick a number above 50 square root of 2, 10,000, whatever it is, you would end up with 10,000 divided by 10,000 squared, which would be 1 over 10,000, which is a fraction. 2 minus a fraction, that would be positive. So we have always decreasing before, right? P is decreasing and then increasing, so we're going to have a global min. So our answer, and again, what are we asked? We're asked to find the least amount of fencing. Now notice they didn't ask me to find L and W. They actually asked me to find the least amount of fencing required. So I want to find the P. What I know is that W equal to 50 square root of 2 is going to be my W that gives me the maximum. My length is going to be, over here, 100,000 over 50 square root of 2. Now what I need to find, though, in this problem, to answer the question that they asked me, is what is the perimeter at that point? What is the amount of fencing? And it doesn't really matter which one of these we use because they're going to work out to be the same. So we would do 2 times 50 square root of 2 plus my 100,000 over 50 square root of 2. Now we might want to go ahead and simplify that. All right, just didn't want to have you sit there while I was calculating this. So we end up with 200 over the square root of 2. So the answer to our question is that the least amount of fencing required is 200 square root of 2, and what units are we in? Inches. Because W equal to 50 square root of 2 makes our perimeter derivative equal to 0, and using modified first derivative, P prime is less than 0 for W in the interval 0 to 50 square root of 2, and P prime is greater than 0 for all W in the interval 50 square root of 2 to infinity, which gives us our modified first derivative test. All right, and then let's wrap up this set of notes by doing one example. Now that I've done several with the modified first derivative, one with the modified second derivative, let's look at one where we end up with EVT. So example 5. We want to find the point on the curve closest to 3, 0. So let's draw a picture here and kind of see what we're doing. First off, we see that this is an optimization problem because we're looking for the closest, the point, I'll circle that, closest to 3, 0. So that's minimizing a distance. Farthest would be maximizing, closest would be minimizing. So we need the curve, so let's sketch that in. So we have our nice x squared curve. So we put that in. Doesn't have to be a great picture. My point is 3, 0, so that's here. And so we're trying to minimize the distance from this point to here. So that's going to be my distance. So I have the point 3, 0, and then I have some point on the curve. So the point on the curve, I'm initially going to label this as x, y. However, given this information, you'll see in a second that the y is not going to stay as a y. So let's talk about our minimizing. So we want to minimize distance, and our distance formula, good old friend from Algebra 1, is going to be the change in x's squared plus your change in y's squared. Now, I am going to tell you this is a shortcut, and this is something that you will always do. It's way easier. Minimizing the square root of something is exactly the same. It occurs at exactly the same spot as if I could minimize the underneath part of that radical, okay? Which is kind of like your Pythagorean theorem. You can minimize the distance squared because that will be at the exact same spot. And we usually consider that to be a little easier, I'm just going to make that y squared, than having to deal with a derivative and a radical in it. So anytime you have a root of stuff and you want to minimize that, you can always ignore the root and minimize the square, and it happens at exactly the same spot. So good tip, nice shortcut. Now look, we have two variables, x and y. I got to find a constraint between them. Now this one students typically struggle with, but do you know a formula to relate your x and your y? Yes, you do. You have the formula. The point lies on the curve. So our constraint that we are going to use to substitute in this problem is y equals x squared. Now again, I could solve it for x, but there's no point. The y equals x squared is going to be fairly easy to substitute that into your primary equation. So your distance squared, let's call that big D, because I don't want to have to worry about taking the derivative. I'm not taking the derivative of that. I'm taking the derivative of big D with respect to x. We plug in plus x squared squared would be x to the fourth. And so that's what we're going to take our derivative of. Now let's think about our relevant domain. And this is where we're going to know that we're going to use EVT on this. Kind of one of those common sense things that we all know that the shortest distance between 2 points is almost, kind of think of it like a perpendicular to the tangent line. So this point, if you think about it, can we pretty much say that it's got to fall between 0, it's obviously not going to be on this side, right? That the distance starts to increase. So we can set 0 to be our relevant domain. We definitely know it's going to be bigger than 0. Could be equal to 0, but we definitely think it's going to be bigger. And then as this point moves away, that at some point you're going to have the point directly above 3, right? That kind of think of this as a triangular situation, that this distance right here, this vertical distance, it's got to be closer in between that. So we can set our x from 0 to 3 and use that as a closed interval test and use the EVT. And again, it's because it's common sense, you know. It has to be somewhere between 0 and 3. You might be able to narrow it down farther, but don't do that. I mean, you just need a closed interval, so go with the blaringly obvious that it can't be, which would be directly horizontal from the point and directly vertical from the point, that it would have to be in between because the median of a triangle would have to be shorter. Think of it like that. All right, so now we're ready to actually do the calculus part. We're going to take the derivative of big D. I could have multiplied this out, but I can use product rule. That's pretty easy with a chain rule. 2, 3 minus x times, don't forget chain rule, derivative of negative x, which is negative 1, plus 4x cubed. I'm going to simplify my derivative so that it's something to work with. 4x cubed, and then we have 6 minus 6, and then minus 2x plus 2x minus 6. All right, so now we might cry a little bit because we have a cubic and I need to figure out where this derivative equals 0. And remember that if it's in a non-calculator section and you've got something like this, remember the whole guess and check that we had before? Just take a look at this. What number for x is going to make 4 times something plus 2 times something minus 6 equal to 0? You can guess and check this one and you can pretty much come up with x equal to 1. Now, once I guess and check and get 1, let's use our old friend, the synthetic division, 4, 0, 2, negative 6, just to see what some other ones are. Drop your 4 down. 4 times 1 is 4. Add these together. 4, add those. 6. 6 times 1 is 6. 0. So that's going to leave us with a factor of x minus 1 and a factor of 4x squared plus 4x plus 6. All right, so when we take a look at this, now it's quadratic. We can check if it factors. We can pull out a 2. That's always nice. 2x minus 1, 2x squared plus 2x plus 3. And does this factor? I could check the discriminant. And if you quickly check your discriminant here, it's going to be negative. There's going to be no real solutions to this. So our only critical value is at x equal to 1. Now remember that we're only interested in EVT, so we're just going to make a chart. And so we just need to do, our big D at our endpoints, 0 and 3, and at our critical value, 1. And so if I plug it into D, if I put in 0, I would get 9 plus 0, or 9. If I put in 1, I'm going to get 4 plus 1, or 5. And then if I put in 3, you're going to get 0 plus 3 to the 4th, which is 81. And then what are we trying to do? We're trying to minimize, so don't just jump for the largest one. We're trying to minimize, and that happens here at 5. Now, let's answer the question. We want to find the point on the curve closest to 3, 0. So the point on the curve, now be careful, you'll be tempted to do 1, 5 here. The x value is 1, and the y value, remember, x equals y squared would be 1 squared, or 1. The point on the curve closest to 3, 0 is 1, 1, because x equal to 1 makes our derivative equal to 0, and by the EVT, it is the smallest distance. All right, so we'll stop this set of notes here because I've gotten a chance to give you an example of using modified first, modified second, and the EVT. And we'll pick this up in the second video to finish out our optimization notes.